Hi everyone and welcome back to my channel. I am Anish and today we'll start the second part of our instruction pipelining topic. Okay, so today we'll learn about hazards in a pipeline. So we have learned what is a pipeline architecture, what is instruction pipelining. So what are the problems that we face? Obviously, if we are gaining so much from a particular architecture, there will be some disadvantages. So this is one of the disadvantages, hazards. Okay, so from the picture you can see that something is going wrong here. What is exactly going wrong, that we'll figure out. So what is instruction pipeline basically? What is the instruction pipeline? Pipelining, which we already know, is used to improve the efficiency of instructions execution by overlapping multiple stages of an instruction cycle. By overlapping multiple stages. So what do you do is simultaneously I am doing some operation for stage 1 on some other data, and also I'm doing some operation on stage 2 on some other data. So in the same clock cycle, stage 1 is also working, stage 2 is also working, stage 3 is also working, stage 4 is also working. All the stages are working. So that's why overlapping. I'm overlapping multiple stages. Okay. We understand this better in the example that will come. Okay, just after this. It is especially useful when the same processing is applied over multiple inputs or instruction. As explained in the previous lecture as well, pipelining will be useful only when we are doing similar kind of operation. Just like I take an example, right, where it was a plus b times some other z variable. Okay, something like that. We are doing that on like different operands, but we are performing the same operation only. Okay, so that is what we do. An instruction pipeline applies the concept of pipelining to the instruction cycle. Okay, we apply the concept of pipelining to the instruction cycle. It breaks the instruction execution into stages with each stage working on a different part. Okay, so up until now what we have studied, I've told you that yes, we will use the pipelining concept. We are doing some different operations, but actually what we do is we do instruction pipelining, because at the starting of a instruction cycle I have explained that instruction cycle has many stages. Okay, namely these are the stages. There can be other as well, I have told that at that lecture, but mainly we will consider these stages. First is the instruction fetch. In the first stage, that is the instruction fetch, where we fetch the instruction. What is the instruction? From where I will get the instruction? PC will store the instruction, right? So I fetch the instruction, then I decode the instruction and I calculate. Like this is just a standard instruction cycle. There can be other types of instruction cycle as well. Don't worry, they will mention this in the question. They will tell you how many stages each instruction cycle has. So next is decode and address calculation. So I will decode the instruction and then I will calculate the address of the operands. Okay, so all those things can happen in stage 2. In stage 3, I will do the operand fetch. I will fetch the operands from the address that is calculated in the previous instruction to our own registers. Then I will do execute. I will perform the operations on those operands. Then I will write back the result. So this is a standard typical 5-stage instruction pipeline. So what I can do, pipeline is a generic concept, right? It can be used anywhere. So pipeline is a generic concept. I will write here. Pipeline is a generic concept and can be used anywhere. Okay, but we are using what? We are using it instructions. Okay, this instruction can be anything, right? This instruction can be anything, addition, subtraction, anything. But net a instruction has total of 5 stages. So I can divide all this into 5 stages and then I can apply my concept of pipelining. So if I apply the concept of pipelining, that particular thing in the instructions of a computer, that is known as instruction pipelining. So this is what implementation of pipelining in instruction cycle. Okay, so let's understand this with an example. Okay, So we have a pipeline execution here. So this is instruction 1. Obviously each instruction can be anything, right? They can be anything, but one thing is constant. They will have always 5 stages. That has been defined in the architecture. They will always have 5 stages. So in the first clock cycle, the instruction 1, the processor will fetch the instruction of instruction 1. Okay, and I have 5 stages, right? I have 5 stages. In the next clock cycle, what will happen? As I have 5 stages, what will happen is, in stage I have kept 5 person, right? One person is responsible for fetching the instruction, other person is responsible for decoding, third person is responsible for operand fetch, fourth execution, fifth write back. So person A now will fetch the instruction of the second I2, right? Second I2, instruction 2. And person B will decode the instruction now of the first instruction. So in second clock cycle, 2 things will happen parallelly. In third clock cycle, 3 things, right? I will do the operand fetch of the first instruction. Person C will do this. Person B will decode the instruction. Person A will again fetch the instruction. Okay. So everything is happening parallelly now. Everything is smooth, right? Everything is happening smooth. So if everything is smooth, once I reach this stage, right? Once I reach the 5th clock cycle, I will do 5 operations parallelly. Okay, everything will happen parallelly. Okay, but what if I tell you there is a problem? Okay, this is smooth. This we have already discussed in the previous lecture, right? Each thing, like after this point, right? I am getting a new output after each clock cycle, right? Because this has done is in 5th clock cycle, I1 is doing write back. In 6th clock cycle, I2 is doing write back. In 7th clock cycle, I3 is doing write back. So at each clock cycle, I'm doing some write back. I'm getting some results. Everything is smooth. But what if it was sequential, right? The CPU knew that I had to first perform I1, I2, I3, I4. Everything was sequential. Okay, everything was sequential, that I had to perform I1, I2, I3 and I4. Now, what if I tell you this I3, right? I3 is a branch type instruction. Branch type instruction. What is branch type instruction? Branch type instructions means basically once I get here, right, I3, it will check some condition, and if that condition is true, it will branch to a new instruction, right? It should not execute I4. It should not execute I4. But I have already done few things. Like I am at this particular situation, right? I have decoded, the control unit has decoded the instruction I3, and it got to know that this is a branch instruction. But the stage 1 already has, person A has already fetched the instruction, right? I4. I4 has already been fetched, and at this particular moment, the control unit has got this information that the instruction I3 is actually branch type instruction. So at this moment, he, you know that word, right? He fucked up. Okay. So I will not say that word. Okay. So now the control unit say, oh my god, now what will I do? I have already continued to fetch the instruction I4, but actually I don't know if the next instruction should be I4 or something else. Let's say it should branch to I7 if the condition is true. Okay. So what will happen here? So a hazard has been caused here, right? Hazard. Why? Because after I3, right, I4 is supposed to not go through if some condition is true. There is some conditional branch. Okay. So we have to see how do we mitigate this hazard. First, let's understand this hazard more. Okay. So instruction I3 is normal instruction. No worries about that. It's normal add operation. So no worries. It is independent, right? Instruction I2 is also normal operation. It's normal subtract of 2 register values on memory location. Okay. Instruction I3 is a branch type instruction. Okay. Its target instruction is 6. Let's say its target instruction is 6, but it will be only executed only if the branch is taken. That is only if the condition is true. Like there will be some condition associated with the branch, like if I equal 1 or I equal 0, something like that. Condition is true. Okay. So what will the person A do? Will it fetch the instruction like here? It is supposed to fetch the instruction here, right? IF. Will I fetch my instruction here? Will I fetch my instruction here for I5? Because if the condition is true, right? If the condition is true, all this is just a waste. This time, right? All this is just a waste. Okay, if I decode my condition, then I got to know, okay, I had to go to instruction 7. So why will I fetch instruction 4 and 5? I will directly go to instruction 6, not 7, sorry, 6. Why will I fetch instruction 4 and 5? It's just a waste, right? These should not have been processed, correct? So we have to, what we do is, the general notation that we follow, or the general, guideline that we follow is, we wait until the condition is calculated. Okay, wait for the condition. We wait for the condition to get evaluated. If it is true, we'll see. If it is true, then we'll fetch the instructions instruction I6, sorry. If it is false, we'll fetch the instruction I4. So we have to wait. We have no other choice than wait. So what we do? How do you solve this? Instruction 3 is a branch instruction. The pipeline must wait until the branch condition is evaluated. When does it get evaluated? In the execution stage. This is just now for different questions, the branch condition can be evaluated in different stages. You will understand by reading the question. Okay, but generally for a standard 5-stage instruction pipeline, the branch condition is evaluated at execution stage. Generally, it can change as well. Okay, so my branch condition will be executed here, right, in cycle 6, because I was here. In cycle 6 only, my branch condition for instruction 3 will be executed. Will be evaluated. So after this particular cycle only, I will be able to know whether I need to go to instruction 6 or instruction 4 or something else. Okay, so actually I have to wait. So I cannot instantly do instruction fetch after this, right? I cannot do. I have to wait for this 3 cycles. Okay, so that I get my information execution, then only I go to the next instruction phase. I have to wait. So I put here stall cycles. It is known as stall cycles. So actually how many stall cycles I have to put here, right? I was supposed to do instruction fetch in this particular cycle, 4 cycle, for the instruction 4, but I'm not able to do. So I will put a stall cycle here. Stall cycle meaning no operation. It is not doing anything. That particular person A is idle. Stall cycle, person A is simply idle. Okay, so here I will write in cycle, this is the 4th cycle, this is the 5th cycle, and in the 6th cycle. So from 4, 5, 6, I will sit idle, right? My person A will sit idle. So cycle 4 to 6, 4, 5, 6, I have to give stall cycles, right? Because at this 6th cycle, right, this is supposed to fetch the instruction I5, but we will not. We will just put a stall cycle. We will not do any operation. It will be no operation. So all this will be just stall cycles. Okay, until the execution phase. All this will be stall cycles. As soon as I get my execution, right, this is internally inside the computer, that as soon as I do the execution and I got to know that my branch condition is what? If it is my assumption is branch condition is true. Okay, this instruction we do some we evaluate some condition, and assumption is branch condition is true. As soon as I got the result, what I'll do, I will directly fetch the instruction I6 after this cycle. I will directly fetch the instruction I6 after this cycle. So I'll go here and fetch the instruction. I will not wait. I will not literally wait. Okay, so that is the case over here. So I will just wait until this execution phase, and after, as soon as I execute this, right, I will directly go to my instruction fetch for the target address. If it was I6, I will fetch the instruction I6. If it was I4, I will fetch the instruction I4. Okay, so actually it is very simple of me to do all this, analyze all this and say, but computer actually is not that intelligent. Okay, computer is not that intelligent. So how do we solve those problems we'll see. Like this computer itself, it won't be able to understand, okay, like as soon as the condition has been fetched, then I will, like, putting the stall cycles is only possible solution. Okay, that is what we do generally, that is what we follow. But without putting stall cycles, if you say that you don't want to put the stall cycles, you directly want to compute this execution, okay, directly want to compute this condition and directly want to fetch the next instruction. So there are a few ways, but generally those we avoid. Okay, we'll see. So this is for the case if branch is taken. If the branch is taken in the 7th cycle, what we'll do, I will do the instruction fetch of the 6th instruction. If branch is not taken, okay, if branch is not taken, what will happen, like this will, anyways, I was supposed to do instruction fetch here, but it will be a stall cycle. I was supposed to do instruction fetch here, it will be a stall cycle. Again, I was supposed to do instruction fetch here, it will be a stall cycle. So how many stall cycles I will have? Total of 3 stall cycles, right? 3 stall cycles I will have. Okay, because my instruction fetch is supposed to be here. Sorry, my instruction fetch was supposed to be here actually, but currently it is here. So how many stall cycles I had to give? Sorry, 2 stall cycles. Sorry, my instruction fetch was supposed to be here, currently it is here. 1, 2, sorry, 3 stall cycles. This also will be stalled, right? So total I will give 3 stall cycles. My instruction fetch was supposed to happen here, but it is happening in the 7th cycle, right? So how many cycles were just abandoned? 4, 5, 6, that is 3. 3 cycles were just kept abandoned, right? They were just stalled, no operation. So if, let's say if the branch was not taken, then I would have fetched the instruction I4. If the branch was taken, then I would have fetched the instruction I6. Okay, so branch hazard introduced delays, stall cycles in the pipeline. In this example, 2 extra, actually this will not be 2, 3 extra stall cycles. Three extra stall cycles were added due to branch condition, right? And the pipeline was emptied after the branch instruction was encountered. So emptied meaning only from this point pipeline again started of filling the water, right? So what happened was that my water was flowing through the pipeline, right? Water was flowing through the pipeline. What happened? There a blockage came. What was the blockage? Stall came, right? This was due to the branch instruction. Okay, this was due to the branch instruction. A blockage came. So a blockage came here, right? And this blocked. This paused all activities. Then again this blockage got over once I got my condition, once I evaluated my condition, right? Then only I took out this blockage, and then again the pipeline was emptied, that is this water was again flowing. That's the meaning, physical significance of this particular thing. Okay, this increases the total processing time as all stages of the pipeline must restart process with the new target address, because basically it increases the processing time, right? So I was supposed to fetch my instruction here, but now I'm fetching it after 3 cycles. So obviously it increases the execution time, which will obviously reduce the processing time. So all this is the disadvantages, correct? Minimizing branch hazards using techniques like branch prediction or speculative execution can significantly improve pipeline performance by reducing or eliminating the need of emptying the pipeline. But this is actually we will not study, and this is very difficult to implement as well. Branch predicting, how will you predict the branch of a particular condition? That is just like gambling, right? You are gambling, so it is very difficult. Okay, so new architecture do this, but there are few methods to this they do. Okay, that will obviously out of syllabus we won't study. So these are few techniques which we do. So basically I haven't told you the basic definition of stall cycles. Now I will tell you the basic definition of stall cycle. Stall cycles are extra clock cycles introduced into a pipeline when an instruction cannot proceed to the next stage due to a dependency, hazard, or resource conflict. Okay, so here, right, actually I was supposed to get my instruction fetch on cycle 4, but I am getting my instruction fetch on cycle 3. Actually one thing is wrong. Okay, this stall cycle, right, here I'm supposed to get at cycle 4, but I'm getting at cycle 7. So how many stall cycles I had to give? This, yeah, 3. So this was the first stall cycle, this was the second, third. So this 3, I had to give 3 stall cycles. The extra clock cycles that I had to give to resolve a data hazard, dependency hazard, or a resource conflict. So we'll learn more about hazards, don't worry. We'll learn more about hazards, don't worry. Okay. During these cycles, the pipeline effectively pauses while waiting for the necessary data or condition to be resolved. Like we pause, right? We pause our operation until the condition has been resolved, then only we resume our pipeline. Okay. This temporarily reduces obviously pipeline efficiency because throughput reduces, right? The overall execution time increases, throughput will reduce. Simple as. So common causes of stall cycles. There can be mainly 3 common causes of stall cycles, or there can be mainly 3 types of data hazards. 3 types of hazards in a pipeline. First is data hazard. An instruction depends on the result of a previous instruction. An instruction depends on the result of a previous instruction still in progress. What do I mean? So we'll go more deeper into this. But let's say instruction I1 is perform R1 plus R2 and store it in R1. And instruction I2 is R1 minus R3 and store it in R3. So actually this instruction I1, during the instruction fetch, I got to know, okay, I have to do like this. I have fetched the instruction. Then during the decode cycle, I got to know I have to perform this operation, right? And instruction I2 has to perform subtraction on same register R1. So this instruction hasn't been completed yet and R1 value hasn't been updated yet. Because what was supposed to happen, that in C programming, right, you will write the code like this: R1 plus R2 and R3 equals to R1 minus R2. So in C programming, what you are supposed to do is this is R3. You were supposed to simply get this updated value, update the value of R1, then subtract from this, right? Subtract the updated value from R3. But here what is happening, as things are happening simultaneously, if you observe here, right, what is happening, I am doing instruction fetch. So here I have fetched that I have to do that some instruction has been fetched. In this decode cycle, I got to know that I have to do R1 plus R2 and store it in R2. Here I got to know I have to do R1 minus R3. Here I am executing that. I have still not updated the value of R2, but here I am doing operand fetch. So I am fetching the value of R2, the old value. Okay. So that's why there is a hazard we cannot do. We have to stop until this write back or execution, depending on the question or how they have given the information. Until then only I can proceed with the next instruction. Else I will not be able to start the instruction. We will come to this. Don't worry. We will come to data hazards, control hazards. What is control hazard? Just what we have shown in the example right now. If a branch instruction comes, it has to wait. Our pipeline has to wait until that instruction has been evaluated. Structural hazard. If multiple instructions compete for the same hardware resource. So multiple instructions are telling that they need the ALU, right? In simultaneously, like what happens in this pipeline, right? All the stages are operating simultaneously, right? All the different stages. But what if in different stages they conflict for the same resource? We'll understand with the example. There we will see that they're conflicting for the same resource. So obviously you are here, right? You are only a single person. Your friend is telling you to go to the sports game, okay, the stadium, and your girlfriend is telling you to go to movie. So you're only a single person, right? Physically. Virtually you can go physically, right? So either you can go to sports movie or either you can go to the sorry, not sports movie, what I am saying, either you can go to the sports or either you can go to the movie. Now you have to decide which one you do. So one thing you can do, first you go to the movie, because your girlfriend will be upset. So first you go to the movie, then you go to the stadium, okay, and go and watch with your friend. So first you are only single resource, right? First you allocate some time to your girlfriend, then you allocate some time to your friend. So that's how resource allocation works. Simultaneously you can do, simultaneously you can do. So that is what this structural hazard is. We'll come to this, don't worry, we'll come to all this in today's lecture only. So if we have stall cycles, right? If stall cycles are there, then what will be my total execution time? So if I have stall cycle, any number of stall cycles, right? Any number of stall cycles of, let's say, n stall. What will be my total execution time? So before finding out the total execution time, first I will write the total number of cycles in pipeline. I'm only talking about pipeline. So what is the total number of cycles? Okay. What is the total number of cycles? Total number of cycles is basically for the first instruction. I will need k number of cycles because k is the number of stages, plus how many instructions are left, n minus 1, because one instruction has already been executed out of n instructions, plus n stall. Okay, because these were supposed to be the extra stall cycles that I needed to provide. Okay, yeah, am I correct? These are supposed to be the extra stall cycles that I needed to provide for the either resolving a hazard basically. Okay, so that is the case over here. That is the case. So now what will be the total execution time? T execution of the pipeline. It is simple, right? It will be basically all this total number of cycles minus 1 plus n stall into TP. That's it. Okay, into TP. So what you have to understand is, like, there is a formula that you can remember, or it's okay if you don't remember as well. What you have to understand, what will be this install? How do you find out this install actually? Let's just take an example. Here my like I was supposed to fetch my instruction here, right? Here, okay, but my execution is happening here. So how many stall cycles I have to provide? Only after this execution only I will be able to start my next next instruction fetch. So I have to provide 3 stall cycles. So if your execution is at the 4th phase, then you have to provide 3 stall cycles, right? Because one cycle is already taken care with the pipeline, because each instruction take 1 cycle only. So that has been already taken care. So if your execution is at the 4th stage, then you require 3 stall cycles. If your execution was at the 2nd stage, then how many stall cycles you would have required? You would have only required, no sorry, 4th. If your execution cycle was here, right, here, how many stall cycles you would have provided? Here, 1 here and 1 here, right? 2 stall cycles. So I hope you are getting a formula. What is the formula? Formula is the execution stage number minus 1. Because 1 is for what? 1 cycle is anyways embedded in the pipeline, because each instruction, each micro operation, or each stage takes 1 cycle. That is already taken care of in this particular formula, right? So what I can say is install, you can remember the formula, or it's okay. It's okay if you don't remember the formula. Install will be like, now it depends, right? When does the branch condition gets evaluated? It can be evaluated in the execution phase stage, or it can be evaluated in decode stage. It can be evaluated anywhere. It depends on the question. If nothing is mentioned, you will assume execution stage. Okay, nothing is mentioned, but generally they will mention. So it is the stage number of branch condition evaluation. Evaluation minus 1. Okay, condition evaluation minus 1. Okay, so that is what my these are the number of stall cycles. Now here, right, something is written. It's that is the same thing is only written here. If the branch condition result is evaluated in the ith phase of the instruction, then cycle ith phase of the instruction cycle, then number of stall cycles due to that branch instruction only, okay, will be I minus 1. Okay, so if no information is given, you will assume it to be in the execution phase. So we write here, if no information is given, then assume it to be in the execution phase. Okay, so yeah, so what are the few impacts of stall cycle? So obviously, right, your total execution time increases. If your execution time increases, then your throughput will reduce, because the number of instructions that you can do per unit time will reduce. Stall cycles reduces the efficiency of pipeline. We'll understand what is efficiency of pipeline later on, don't worry. As it increases total execution time, this is intuitive, right? I hope you understand. Fewer instructions are completed per unit time due to idle cycles introduced by the stalls. Hence there is a reduction in throughput. So these are the like consequences of stall cycles and hazards. Okay, these are the disadvantages of a pipeline. So obviously we have to make do with that. So we'll solve this question from there. The concept of stall cycle will be cleared more. Okay, consider an instruction pipeline with 5 stages without any branch prediction. So we don't do any branch, we don't predict the branch. Okay, we have to wait for the evaluation of the branch condition. Fetch instruction, decode instruction, fetch operand, execute instruction, and write operand. So this is a standard 5-stage instruction cycle. They will tell you how many stages it has, and also they will tell you the stage delays. Also they have told this there are intermediate storage buffers as well. Each stage and delay is 1 nanosecond. Okay, everything is mentioned. A program consisting of 12 instructions is executed in this pipeline processor. Okay, instruction I4 is the only branch instruction and its target branch is I9. If the branch is taken during the execution of the program, the time needed to complete the program. Now here they have not told me that at what stage I am executing or evaluating the condition of the branch. Okay, so what are they telling if the branch is taken? So I will assume obviously at execute instruction I am evaluating the condition. So I write down the data points. My K is 5. It is a 5-stage instruction pipeline and it doesn't have any branch prediction, and my TP will be max of 5, 7, 10, 8, 6 nanoseconds plus the registered delay, right? What is the registered delay? Delay of each buffer is 1 nanosecond. And I have 12 instructions. So this will be 10 plus 1, so this will be 11 nanoseconds. Okay, and I4 is the only branch instruction, and my assumption is, what is the stage or phase where I am evaluating the condition execution, right? So what is this phase? This is the 1, 2, 3, 4th. At 4th phase I am evaluating, assume at 4th phase evaluating condition. Okay, so how many stall cycles I need to give? 3. So n stall will be 4 minus 1, that is 3. How did this 4 minus 1 came? I have explained. I will not waste my time here. Okay, so what will be the what are they asking? Total time. So what is the total number of cycles actually? Total number of cycles, n cycle will be what? It will be k for the first instruction. And they have also told me that actually branch is taken during the execution of the program. So directly from I4 I am going to I9. So total I have 12 instructions. So 12 instructions I have, and out of those I'm executing I4, but I'm not executing I5, I6, I7, I8. I'm directly going to I9. Correct? I'm directly going to I9. Just hold on. One thing I want to check. Yeah, this is fine. So I'm skipping this 4 instructions, right? So out of 12, I'm skipping 4. So I'm only, my pipeline is only executing 8 instructions. And I had to give stall cycles as well. So that I will compute later on. So this is n actually, number of instructions that the pipeline is executing. K plus n minus 1 plus n stall. So k is already given, k is 5. Okay, so this will be 5 plus 8 minus 1 plus 3. So this will be 13 minus 1, 12 plus 3, 15. So total it is taking me 15 cycles. Okay, now what will be the execution time of the pipeline system? The execution time of the pipeline system will be n cycle into time taken by each cycle, that is TP. So it will be 50 into TP is 11 nanoseconds that we have just computed. So it will be 165 nanoseconds. So option B will be answer. So these type of simple questions also come in hazard side instruction pipelining. Okay, this is a basic hazard question. Okay, now we'll go more deeper into the hazards concept. So pipeline hazard, right, are what are situations that disrupt the smooth execution. So everything was happening smoothly. At each cycle I was getting a new, I was able to execute a new instruction, only I was taking one extra cycle, but I had to put stalls because there were some problems in the execution of the instructions, right? Multiple instructions. What were the problems? Problems were like branch prediction, branch was there. Data dependency also will be there. Now we will study the data hazards and structural hazards. Structural hazards means same resource. Okay, so we'll see that. So what happens? It leads to delays or inefficiencies. Okay, so hazards, these are actually what? These are problems. These are the problems that I face while implementing my pipelining, instruction pipelining. Occur when the next instruction cannot execute in its designated clock cycle due to some issue, right, like branch prediction or something. These delays introduce stall cycles, also called as pipeline bubbles. Why pipeline bubbles? Because my pipe, right, pipe was supposed to be smooth here, like water was supposed to flow smooth here, but there were a few bubbles here due to hazards. It got stopped. Bit of water flow got stopped at that particular region due to a hazard. Okay, that's why it is known as bubbles, pipeline bubbles as well. Okay, so this things we learned. There are mainly 3 types of hazards. Okay, so first one is the data hazard, or also known as data dependency. So let me take an analogy. Okay, in a team, person A is working on task 1 that produces data for person B's task 2. So you are working on a project. Okay, so like what happens? Let me give you an example of a in the semiconductor industry, right? So I am designing a particular chip. I'm designing a chip. Okay, if I don't design the chip, then how will the person, like I am designated to design the chip and person B has been designated to test the chip. Whatever I have designed, he or she will test the chip, right? If I am not able to design the chip, how will the person B test the chip, right? If I have not even designed the chip. So there is some data dependency, right? Only until the time until which I am able to finish designing the chip, then only that person will be starting his test, right? Else how will he or she start the test? So that person has to wait for me to finish my task, then only that person can start his or her task. Okay, so there is a data dependency between the two tasks, two instructions, right? That is what is happening. Person B cannot begin task 2 until person A finished task 1, causing a delay. In pipelines, data hazard occurs when one instruction depends on the result of the another instruction that is still in execution, still in progress, causing a stall until the required data is available. Okay, just like that, right? I told you, right? An example. Let's take example here. Here, this occurs when the instruction depends on the result of a previous instruction that is still in the pipeline. Instruction 1, add R1, R2, R3. So I have to add R1, R2, R3 and I have to write the result in R1. Then instruction 2 tells me to subtract R4, R1, R5. So what it does is it reads from R1, right? It writes to R1, it reads from R1. Okay. So we subtract R4, R1 and then store it to, we do something, right? We do something, add something and then store. Okay, that, but important point is we are writing back here to R1 and we are reading from R1, right? So what was supposed to happen is that I was supposed to update my value of R1, then I use that value in the second instruction. But if I simply do the pipelining, right, there will be some problem. So like what it is doing R1 like is storing the value R2 plus R3 and my R4 is basically R1 minus R5. Okay, so obviously I had to use this updated R1 value here, but if I just simply use my pipelining, what will be the problem? Let's see. First I will fetch the instruction I1, it has been fetched, then I will decode, control unit will decode, and simultaneously I will fetch my instruction I2. Here I will do the operand fetch. So what will this operand fetch do? It will fetch R2 and R3, right? That's what it will do. Okay, and here I am decoding in the instruction. So control unit understands that, okay, I have to do what? I have to simply perform subtraction operation. That is what this decode operation understand. This is addition operation. Here I am executing. So here the ALU will be in use where it will execute R2 plus R3, and let's initially assume that initially R1 was equals to 0 initially. Okay, and here, right, what was supposed to happen? Here operand fetch was supposed to happen, right? After decode, operand fetch was supposed to happen. If I do operand fetch here, what I will fetch? I will fetch the operands, right? I will fetch R1 and R5. So currently what is the value of R1? You will say currently the value of R1 is R2 plus R3. I will say wrong. You are wrong. Why? Because I have not updated the value of R1 yet. This is the stage where I update, write back. At write back, I update the value of R1. I computed, I evaluated my operation, and then I have to write back in the 6th cycle. I haven't yet written back to the register. So if I do the operand fetch here, it will simply fetch R1, that is 0, and R5 will be still there. R5 will be some value, which is wrong actually. I don't want this. I wanted R2 plus R3 here, right? I didn't wanted this. So that's why I cannot simply have a operand fetch here, right? Cannot fetch the operand here because I will fetch the wrong operands. So here I will fetch the wrong operands. Okay, So I have to wait till write back. After this write back only, the operands will be updated. Registers will be updated. Okay, so after this only, after the 5th clock cycle, I will start my operand fetch. Okay, after here only. Actually what we do, there is a term known as operand forwarding. As soon as I do the execution, right, it can actually directly forward it to the next instruction. There is one shortcut. Okay, there is one shortcut, so that's why I have only put one stall, but I have a basic idea you have got, right? So after this write back, I am supposed to start my operand fetch. I cannot simply start my operand fetch here. Decode instruction can be here, but operand fetch I have to wait till write back, or there is a concept known as operand forwarding that I will come to in the next few slides. That does what? That after this execution, right, that instantly gives it to the next instruction. So now let us understand with the example what will be the exact problem. Okay, so here, if let's say for 3 cycles, right, my initial values are given. Okay, for 3 cycles, first, second, third cycle. This assumption, this is not exactly this first cycle. I'm just assuming initially the R2, R3, R5 values are this. So initially I want to perform what? Actually, what result should I get? What do I want to perform? I want to perform this operation and this operation, right? So actually what should have happened? So correct scenario. So in the correct scenario, what should have happened is, first I should have added R2 and R3, okay, and stored it in R1. So R1 equals to, like I will write here the operations, R1 equals to R2 plus R3, and R5 is equals to R1 minus R4, I believe, R4 or something else. Sorry, R4 equals to R1 minus R5. So what I can say, for this first cycle, R2 plus R3 will be 3, right? 1 plus 2, it will be 3, and R4 should be R1, this is 3, minus R5. R5 is also 3 here, right? In the first cycle, R5 is also 3. So it will be 0. Okay, this is the cycle 1. And in next cycle, what should happen? In next cycle, again, the values of R2 and R3 and R5, all of them will be updated. So R2 will be 4, R3 will be 5. R2 will be 4. So my what will be my R1? R1 will be 4 plus 5. Equals to 9. And what will be my R4? R4 will be 9 minus R5. R5 is 6 equals to 3. And in cycle 3, my values will be what? R1 is equals to 7 plus 8. So it is equals to 15. R4 will be equals to R4 will be equals to this 15 minus 9. Okay, 15 minus 9. So that is the case over here, right? Now what you should understand is that this is the correct scenario that should happen. The result that I'm expecting 3, I'm expecting 0, I'm expecting 3, and expecting 9. But what is actually happening? Actual scenario. What is actually happening is very different than what should I get. So for that, right, I will actually take this picture with me. so that you will understand this better, and obviously the cycle as well. Okay, this I will reduce. And the table as well. So I'm assuming this cycle 1 represents the cycle when the operands are fetched. So here I have fetched my operand of the first instruction, right? First instruction should do this R2, R3 and R5. This should fetch this operands. So the instruction I1 has fetched all this, right? So in the cycle 1, okay, or in the instruction I1, what will happen is it will fetch R2 equals to 1, R3 equals to 2 and R5 equals to 3, and obviously store in its own general inside register, right? Own registers. It has fetched the operands. After fetching the operands, it will go into the execution phase, correct? And it will execute what? It will execute R1 equals to R2 plus R3 and R5 will be equals to this is the first instruction, right? That it will do. Okay, this is only the instruction that it will follow. Okay, because what we assumed I1 instruction to be, I1 instruction was supposed to be only adding R2 and R3, right? So it will add R2 and R3. Okay, but the problem is simultaneously as I'm doing this execution, I am fetching the operands, right, for the second instruction, that is for the subtraction. That should not happen. Actually, I only should fetch the second operands after finishing this addition, because this R1 actually is dependent, right? After only the value gets updated, I should use in the second instruction. I should not use the old value. So what will actually happen is that in the instruction I2, it will fetch the operands. It will fetch what? It will fetch, like, it doesn't need R2, it only, okay, this also doesn't need R5. It only needs R1. So what operands it will fetch? It will fetch R1 equals to 0. Why it will fetch R1 equals to 0? Because initially, if nothing is mentioned, I have assumed all the initial values of the registers to be 0. So it will not update the value here, right? R1 was supposed to be R2 plus R3, but it will not fetch R2 plus R3 because this operation hasn't been completed. ALU needs some time to complete the addition, right? Simultaneously, we are executing and fetching the R1 operand, okay? So R1 hasn't been updated yet. So what I do is I fetch R1 equals to 0, and obviously R5 was initially 3 only, correct? R5 was initially 3 only. So we fetch R5. So now what it will perform in its instruction to execution cycle, it is supposed to perform R4 equals to R1 minus R5. So we will get answer -3. Was I supposed to get -3? No, I was supposed to get 0. I was supposed to get 0, right? But I got -3. So it will go on like this. Why is there any problem? Because before updating the value, I am taking the operand, right? I have to update the R1 value, then only I should take the operand. If I update the value later and I take the operand before, obviously I am not using the latest value. I am using the old value. That calculation is wrong because I was supposed to get 0, but I'm not. So that's the advantages of sequential processing, right? Sequentially, if something is dependent on the previous instruction, right, it only finishes the previous instruction, then only comes to the current instruction. It doesn't do everything simultaneously, like stages of everything currently, because this stage execution or operand fetch is dependent on the previous stage execution, just like branch type instruction, right? So there is a data dependency of the previous instruction. So what is happening? There is data dependency of previous instruction. Okay, so that is the problem for this. Okay, so one more thing I am able to explain you, and it is taking you so much time to understand, right? So pipeline itself doesn't have any intelligence. it is very dumb, like computer is very dumb, right? So pipeline is not that intelligent to understand where is their data dependency. Okay, so pipeline or the architecture itself cannot understand if there is some data dependency or not. It is very difficult for us to find out data dependency. Okay, if I find out, okay, I got to know that there is data dependency here. So what I will do, I will just give a stall cycle here, right? After the execution phase, only after this I will do the operand fetch, correct? So that is the problem. Pipeline itself doesn't understand if there is a data dependency or not. Okay, so pipeline I will write here, pipeline by itself won't be able to understand won't be able to identify data dependency on his own. Okay, so obviously someone has to identify this. Who identifies this? Okay, so the compiler helps in this. Compiler helps. Okay, the compiler understands the instruction, so it adds stall cycles or NOP. NOP means no operation, or it performs or some instruction which are not interrelated. So what do I mean by that? So what happens is, if I have a C code, right? Let's say this is the C code. Int I equals to 5, I plus plus, then while I not equals to 7, do something, right? Like x equals to y plus z, and initially there were some values, right? X equals to y equals to z equals to 0. Okay, something like that. You do something like this. So what we do is, compiler breaks it down into smaller micro operations, right? That is the task of the compiler. It breaks it down. Then what it does is, it understands if there is a data dependency between the previous micro instruction and the current micro instruction. So if there is, compiler is a smart person. Compiler is smart, not like us. He is a very smart person, he or she. So it actually gives a stall cycle between these two micro operations. Okay, and sometimes what it can do is, in this particular cycle, right, if we want to utilize this cycle, because this cycle is just idle, what we can do, we can do this instruction, check this instruction. If like there is a data dependency here, so we can just check this instruction, right, or something like that. It will do, but most cases it will do no operation. No operation means just idle. It is sitting idle. It is not doing anything. So here, just understand this. Data hazards are very, very dangerous. First thing is hazard, but we will also be able to not know if there is a hazard or not, because our results were getting wrong results, but only after me doing manual calculations and comparing with the actual values, I'm understanding, okay, I'm getting wrong results. But this, if you are in the CPU and just doing some computations, right, you assume that computer always gives the right answer. So how will you know that you are actually getting the wrong answer due to the data dependency or hazards? So obviously we have to add stall cycles. Compiler adds the stall cycles. So here, like that is only written. A standard instruction pipeline cannot detect data dependency on its own. The detection and resolution of this dependency often require additional mechanism. So first one I have explained, that is a software mechanism, that is like compiler. Okay, so software solutions, delayed load. The compiler rearranges the instructions to introduce NOPs, no operations, or non-dependent instructions between the dependent ones. So here, what we do, we add a between the instruction 2, right? We add a no operation. No operation, right? It also has all the 5 stages: instruction fetch, decode, operand fetch, execution, write back. But it is not doing anything. Literally, it is not doing anything. Okay, just there is a dummy operation. We can also say it is a dummy operation which has no use except just giving a stall cycle. That is the only thing. Dummy. Okay, this allows sufficient time for the previous instruction to complete and avoid stalls. Okay, so that is the case over here. So there can be hardware solutions as well. What is the hardware solutions? Hardware solution is what we can do is we have a opportunity. What is the opportunity? As soon as the execution phase is done, right here, as soon as I execute the value, I instantly send it to the next instruction. Okay, I don't wait for the write back. Because after execution, right, I store it into a register. Remember, we have a buffer register to store between the stages. So I instantly give it to the buffer register, and buffer register instantly give it to the operand fetch. Okay, we don't wait for the write back. So that is what we do, because for currently what we have to do, we have to wait for the write back, then only I can do the operand fetch. This is also wrong. Operand fetch should be here actually. Okay, so currently what we're doing is I have to wait for the write back. This will be again stall. This will be operand fetch. This will be execution. Currently I have to wait for the write back. It writes back to the register R1, and then only I will do my operand fetch after this. But we have a hack for this. What is the hack? So this also is wrong, right? Actually, operand fetch, execution, and write back. So what we do is we bypass the write back stage. So what are they telling in team? Let's take the analogy. Person A can share the data as soon as it's available, even before completing the task 1 fully. So person B can begin with task 2 without waiting. So I have a project, right? And in the project I have to do some simulations and some things. Okay, so what I have to do, I have a manager, so I have to show my manager my work. Okay, just hold on. This charge is not happening. Okay, this plug got out. That is the problem. Just 1 second. Oh, it's fine. So what I was saying is, just hold on, I will check if everything is fine. Recording, yeah. I have to tell my manager, show my manager that this is the design. I have to create a PPT, then show him. One thing I can do, as soon as I design my, let's say I am designing a amplifier. As soon as I design the amplifier, I don't wait for any documentation or just PPT creation something to show my manager. I instantly send it to the person B. Okay, for him to start the task. I don't wait for approval, right? I know this is okay, this is correct, so I will send it to directly to person B, and he can start his work, and in between I will create my PPT and all those things. So parallelly we can do all these things, right? So that is what this means by forwarding, operand forwarding. So in the team analogy, person A can share the data as soon as it's available. As soon as I complete my building of amplifier, I don't wait for PPT creation, I don't wait for documentation, I don't wait for approval. I send it to person B for him to start his task. He can begin his task without waiting. So this is the concept of operand forwarding or bypassing. Allows dependent instructions to use data directly from the previous stage without waiting for the write back. Okay, without waiting it for it to be written back to the write back stage. Directly from the execution stage, I can directly send it. Okay, so that is what we do. So what we do here is that we don't wait. Okay, even though we have done operand fetch here, this execution actually takes the data from this execution. We do some operand forwarding. Okay, so it is an internal hardware mechanism. what happens? Basically I have registers, right? After the execution finishes, I have registers in the stage 1, right? This was my stage 1 and here I had a register. So what we do, like stage 2 has two options. Stage 2 has two options. Either take the operands from the memory or take it from the registers. So what it will do, it will take the operands directly from the registers. So it is internal hardware mechanism, very difficult to build, but it is a one way to avoid this data hazard. Okay, so we take the value from this execution, output of the execution, to the input of the next execution stage. Okay, so here we bypass the write back stage. So that is what operand forwarding is. We take the value from previous execution stage. Okay, forwarding from previous execution. So this is my operand forwarding. Operand forwarding is. So we take, like this is also known as the buffer register. We directly take from the buffer register. So here what I will say is we directly take the operand from the buffer register. We don't wait. Okay, we don't wait for it. So that is the important point that I wanted to talk about. Now there is an important thing. Okay, this is only possible when I am doing some ALU to ALU operation. Okay, no stalls will be introduced. But if I am doing some ALU to memory operation, operand forwarding, stalls will be introduced. What do I mean by ALU to ALU and ALU to memory? Okay, what do I mean by that? So I will explain that. Just hold on a second. Yeah. So what does ALU to ALU mean? Here, right? Whatever, like in the next stage, where do I need the data? Next instruction was R4 equals to R3. R4 was stored with R1 minus R4. So all these, right, are present within the ALU because they are general purpose registers, and we know GRPs are within ALU. What if I told you to do this? Memory location like R3, like this. What if the instructions are this, right? First my M1000 equals to R2 plus R3, and R4 equals to M1000 minus R5. Now can I use can I use operand forwarding here? Can I use operand forwarding here? The simple answer will be no. No, why? Because actually I am not like storing this addition value in a register. Okay, previously I was storing it in a register, in the pipeline register somewhere, but now I am actually not storing it in a register. The instruction has said me it is not storing it in a register. It is storing it some memory location. Okay, we are storing it in a memory location. So I cannot instantly take from this memory location value, right? I cannot, because accessing memory location is very, very slow. It takes time to access the memory. So if I am doing some ALU to memory operation, operand forwarding is not possible. We have to introduce stalls only. So we don't have any other way. Okay, so operand forwarding here will not be possible. Don't worry, we'll understand this more with questions. Questions will come there, we'll understand this more better. Operand forwarding not possible. Okay, so that is the case. So sometimes what we do is we introduce hardware interlocks that actually has the capability to detect the hazards. It can detect the hazards and introduce stalls until data dependency have been cleared. So it will introduce stalls until data dependency has been cleared. So like it is just like software where the compiler understands that there is a data dependency and it gives some no operation or stalls. Here the hardware will give some no operation and stalls. Okay, so that is the thing. Like, why is it called hardware interlocks? Because each of the instructions, right, each of the stages, each stage has a log associated with it. So what happens as soon as I do the operand fetch, right, and I understand in the next instruction that I have to use the operands of the previous instruction, not instruction phase, sorry, in the decode phase, that I have to use the operands of the previous instruction. So I put a lock here. Lock. So this, like the next instruction, right, will not be able to use this operand fetch until the lock is unlocked. When will the lock be unlocked? Here, right? Here, that after the write back only, this will be unlocked. Okay. So actually this also should have been a stall only, because after write back only, like it depends, right? Sometimes in the question they tell you at write back the register actually is written, at execution sometimes also ratio is written. It depends how the question is framed. So you will solve according to the question. You don't know whether you have to provide one stall cycle. If I have provided only one stall cycle and I'm doing operand fetch here, my assumption is that in the execution phase itself the data has been written to the register. That is my assumption. Okay, I can be wrong as well. Okay, it depends on the question. So like, also you can understand with this analogy that we have blocked the pipe. The pipe is currently blocked. Okay, so you can understand this as well. Now there are many types of hazards. Okay, so one is read after write. Like there are many types of data hazards classification. So first one is read after write. So whatever this written, right, this actually what actually needs to happen but is not occurring. So this is the thing that actually needs to happen. Okay, that actually needs to happen, needs to be done, or needs to be done. What do I mean by this? Once we see the example, we will understand. This is also known as true dependency. Why this is known as true dependency, we will understand this with when I compare it to the other types of hazards. In short, this is also known as raw. Okay, raw, like that. So definition: a raw hazard occurs when an instruction J reads a value from a register or memory location before the previous instruction I writes on it. The example that we have just used. So instruction J, that is this second instruction, gets the old value instead of the updated value from the instruction I. So I have instruction I, right, where my R1 is A plus B. Okay, R1 is A plus B and my R2 is R1 into C. Correct. So if I am using pipeline instructions, it will take some time for me to execute, right, and update the value of R1. But before updating the value of R1, I am using this R1, right? Initially R1 was 0. So I am using this R1 here. So there is a dependency between this previous instruction and the current instruction. So I am reading the value of R1 before it gets updated. So read after write. What I should have actually done, after writing, I should have read the value of R1. Okay, but I am not doing it. So that is what it means. Read after write means I am reading it after write. That should actually would have happened, but I am not doing it. I'm not doing it. I'm not reading after writing. I'm reading it before writing. That is the problem. What should have actually happened? I should have read it after writing, but I'm not able to do it. Okay. So here, like the same example is given only. Assumption, just understand in the question it will be given that assumption is, just understand one thing, that assumption is that at execution phase, the GRPs, right, or the general purpose registers gets updated. Because general purpose registers are connected with ALU, so it will not take me much time. Here write back, right? Write back generally is write back to the memory. Okay. Execution, it executes the value and stores it in general purpose register or ALU. So it is internal to the ALU. So that's why assumption is my operands are ready for after this execution phase only. That is my assumption. Okay. In the question it will be given. We'll solve questions. You will see. Don't worry. We'll solve the questions. Okay. So here what happens? J needs the value of R1. But R1 is updated in the, actually not in the write back stage, in the execution stage actually. Okay. In the execution stage. That is my assumption. Not in the write back, in the execution stage. If J reads R1 prematurely, if I read R1 here, right, even like before the execution stage has completed its operation, what will happen? My second instruction will get the previous value of R1, not the current updated value. So I am not doing read after write. I'm not doing read after write, right? So that is what is written. R1, it will get the old value. Old value of what? Old value of R1. Okay, so that is the one issue that you should know. Then is read after write. Read after write. So how we can negate this read after write problem? So we can use operand forwarding that I have just explained. What we do is, after this execution phase, right? After the execution phase, what happens? It is written to the registers. So as soon as it's written to the register, I send it to the next stage. Okay. Actually, this is I send it to the execution phase of the next stage. So here I send this to the execution phase of the next stage. So this execution stage, right, of the second instruction, it uses operands from the previous execution and not this. It does not use this. Okay, so this is just a waste. This is also like a stall cycle. This is just a waste, right? So we use the operands for this execution from the previous execution phase. After executing, operands are ready, right? Operands are ready here. Okay, so I instantly send this operand here. I instantly send as soon as the execution phase is done, right? So that is what we do in the operand forwarding. But remember, this is only possible because this is a ALU element, right? R1 is a general purpose register, that is a ALU element, and this is also a ALU element. R2 is also a ALU element. So I know ALU to ALU operation is very fast. I cannot do something if it is stored in memory. I cannot do that. Okay, I cannot do that. So just be careful about that. We will do questions that we will understand. Also, we can introduce interlocks which stalls until the I completes, until the write back phase of the I we stall. That we can do. Okay, anything. Now there is another type of data dependency that is known as write after write. So this should have actually happened, and this is also known as false dependency or write dependency. Why is this false dependency? I will explain that. So in instruction I am writing on R1 A plus B, and in instruction J, that is the second instruction, I am writing on R1 R2 into C. So finally what value I should get? Let's take an example. Let's take A equals to 2, B equals to 3, and C equals to 4, and R2 equals to 1. So actually what I should have gotten, I should have gotten my R1 equals to A plus B, that is 2 plus 3, it will be 5. Then I should have updated my R1 equals to R2 into C. R2 is 1 into C is 4, that is 4, correct? Now tell me, pause the video and comment below, does this second instruction J, does it need to wait for the previous instruction? No. to calculate all this, right? Do I have any dependency previously? No, I don't have any dependency. It just overwrites whatever was previously written. Do I care about this value? If I would have cared about this value, I would have stored it somewhere else. If I would have cared about this previous R1 value, I would have stored it somewhere else. So if I really need this value, I will store. We can store. I will just write it here. We can store it in some other register if I really need this value. Okay, so that is a case over here. If I really need, I can store it in some other register, but actually I don't need. I don't like the user may have known, right? That's why he is overwriting it. Okay, so both instructions write to R1. If J completes first, then its results override the correct value computed by I. So do I care about this? No. Okay, I don't care about this. So that's why this is known as false dependency, because the previous instruction actually, like the current instruction is not depending on the previous instruction. Yes, there are like registers which are same, which are getting used, operands which are getting used in the previous and the current instruction, but there is no actual dependency per se, true dependency. This is false dependency because I don't care about this. So even if I do execution here, okay, this is a bit wrong. Operand fetch is here. Okay, this right. This is again wrong. This should be decode instruction, operand fetch. Execution and then so even if this has written back something, do I care? Do I have to wait for this execution phase? No, right? I can fetch the operands because these operands are totally independent. R2 and C are totally independent of the previous operands, right? So I can totally fetch R2 and C here and I can perform my execution and then I write back. I don't care whatever was written there previously R1 because finally I want this value only. I want this value only. So it doesn't matter. Okay. So I can show you an example as well. Okay. So like here I've shown you example only because at the end I want 4. Previously my R1 was supposed to be 5 here, but I don't care about this. Finally I care about this only. So R1 is 4 only. So I don't care about this. Okay. So that is the important point that I wanted to talk about. So here its analogy is given. Two people are editing the same shared document and the second person saves changes before the first person completes the edits. Will it change anything? No, right? Obviously the second person can also save the edits. Okay, so it doesn't, there is no actual dependency. So what is the solution? Because if I want to really store this value, right, previous value, I will just store it in some other register. So we do register renaming, allocate separate registers to avoid conflict. If I'm writing after write, so I will allocate this separate register so that it doesn't override the previous value. Okay, that is just simple solution. Compiler can do these type of solutions. Okay, so this change has been changed to from R1, this has been changed to R2. Okay, that is what we do. Next type of dependency, only there are 3 types of dependency, is write after read, war. We are going on a war. Okay, that is also known as anti-dependency. We'll understand this. So a war hazard occurs when an instruction J writes to a destination before a previous instruction I has read from it. So what should have happened? Write after read. Only after reading I will write to the register, but I have already written to the register. That is a problem. So here what is happening is I have instruction I, that is R2 is equals to R1 plus B. R2 equals to R1 plus B. And R1 is equals to C minus D. Okay. So what I am supposed to do is I am supposed to read from this R1. Okay. First and then add these two up and then store. Okay. Store. So what was supposed to happen is, let's say R1, I will take the same example only. R1 is 1, B is 2, C is 3, D is 4. Okay, these are the things. So R1 is 1, B is 2, C is 3, D is 4. Now what if happens, like what should have happened is R2 should be equals to R1, that is 1 plus 2 equals to 3, and R1 equals to C minus D, right? So C is how much? 3 minus 4, that is minus 1. This should have actually happened, but due to some glitch, some problem, first I should have happened and then J, right? But due to some problem, J is happening, then I is happening. Then what will be the problem? Then my R1 will be equals to 3 minus 4, that is minus 1, and my R2 will be equals to R1 plus B, right? R1 is what right now? R1 is minus 1 plus B. B is 2. So it will be 1. So actually I am not getting the correct answer here. I should have gotten 3. R2 is equal to 3. I am not getting the correct answer. So that is why I am writing, like I should have written after read. I should have read this register first, then I should have written, but I am not doing it due to some problem. Okay. So that is the problem. That is the hazard. But will it actually happen ever in a pipeline system? No, right? It will never happen. That's why this is also known as anti-dependency or false dependency, because everything happens sequentially. This is also known as false dependency because yes, this is correct. Dependency. Yes, it is correct. It is correct that there is relation between the previous instruction and current instruction, right? There is some shared memory between the previous instruction and current instruction, but that is actually a false dependency. That is not a problem to us because obviously I'm reading that here first, then I'm writing it. That is totally allowable. So what we do is, this is actually R1 equals to A plus B and A equals to C minus D. They have given some other example. Okay, that is the problem. This should not, this is wrong actually. A lot of things are wrong. Okay. So R1 equals to C minus D. So here what is happening is it a problem? So I'm doing the instruction fetch, then decoding, then doing the operand fetch. So I'm reading R1. Reading R1. And here I'm decoding the instruction, and this is actually wrong again. This is wrong. And this is also should not be execution, this should be operand fetch, and this should be execution. So here what is happening is I'm reading from R1 and operand fetch is fine. All these are independent. All operands are independent. Okay. And I'm doing execution. Execution will do what? It will write into R1. So obviously I'm reading before writing, right? Write after read. So every time A is there, so it will be always write after. It will always after. So I'm writing on R1 after reading. So it is totally fine, right? It is totally fine. It is totally fine. Okay, there is no problem with this. That's why this is known as false dependency. We don't need to add any stall cycles, nothing. We don't need to do anything. Okay. So like what happens is, like what is the analogy of real life? Someone starts erasing content from a shared notebook register before their friend finishes reading it. Okay. The problem would have been if like what we have both Ramesh and Suresh have a shared notebook. They go to class and they write on the notebook. Okay. So Ramesh will study that subject first, then Suresh. So what happens is Suresh first studies that from the notebook. Okay, we have only a notebook, single notebook. Okay, Suresh first studies from that notebook and he studies, right? He has finished his study, Suresh. Then he gives it to Ramesh, and then Ramesh is a bit smarter than Suresh, so he writes like he edits the notebook, right? He writes the things that he have understood better or in his own language. So he writes on the notebook, Ramesh. Will it be a problem to Suresh? No, because Suresh already has completed his study, right? He has already completed his study. So it's okay if Ramesh does anything with the notebook because Suresh has done his job. So he doesn't need to go back to the notebook. Ramesh can write, do anything. So that's why write after read is a false dependency. There is no problem of me writing after I have already read the register. But what would have been a problem? What would have been a problem? If Ramesh would have told Suresh, okay, just give me the notebook first, I will read first, okay? But he edits the content, he changes the content, he erases the content. Then he gives back to Suresh. So few content have been removed. So Suresh will not be able to completely study the subject because few topics have been removed by Ramesh. So then it's a problem. Okay, but the sequence should always be followed. Suresh will get first, then Ramesh. But due to some reason, sequence is not followed, then obviously you will have dependency, you will have a hazard. But generally, there will not be an hazard because if you follow sequence, everything is sorted. So that is what is written. If I don't follow sequence, this is written. This analogy is written according to the not following of the sequence. If I don't follow the sequence, then this will be a problem. Okay, provide each with their own copy. Again, what you can do is to have this, they should not share the same notebook. I can take a print out of the notebook and share it to both Ramesh and Suresh. They can do whatever they want. Okay, so we do register renaming same as previous dependency. If this problem happens, if this hazard happens, okay, so we can use a temporary register to store the intermediate value. So R1 can be used as a temporary temp1 plus b and temp2. Okay, all this like we can do simple register renaming. Okay, so what we need to understand is how many cycles can data hazards affect. Okay, can I calculate that? So here I am giving you a question. I have in each cycle I am doing these type of operations, right? In each cycle I am doing these type of operations. Now can you tell me how many cycles I need to wait here? How many cycles I need to wait? Can I find it out? It depends, because here where is data dependency? Where is the data dependency? All these are different registers, but here I am observing I need this value of register R1, and R1 previously getting used. Yes, R1 is previously getting used actually. So from here I am using R1, correct? So I am using R1 previously. So there is a data dependency. Now can you tell me what type of data dependency is this? Data dependency. What type of data dependency is this? Can you tell me that? So this data dependency, right, is basically just see what is happening and just see it. Okay, so what I am doing, I am writing, not that, I am reading from this register after write. So after I have written it here and I am reading from it, right? I am reading and incrementing it. So I'm reading after write. So this is a raw type of data dependency. I'm reading after write, which is a true data dependency, which is a problem. Okay, so it depends, like how many cycles can it affect, how many stalls I need to give. It depends, like I have this many number of instructions in each, after each cycle this many number of instructions are happening. So to answer this, the simple answer will be it depends on the number of stages of a pipeline. Okay, because in between, right, this many instructions are happening. So if I have 3 instructions that are already happening and I have enough space between these 2 dependencies, then I don't need to provide any stall or no hazard will be caused. But if there is not enough space, right, if this instruction is directly here after the first T1 clock cycle, then I may need to provide clock cycle stalls. Okay, it depends. We'll see a few questions and from that we'll understand how many stalls we need to provide. We'll understand this. Don't worry, we'll understand this. So this is a summary basically of different types of data hazards. Okay, summary of different types of data hazards. You can read this, go through this, and like remember and put it in your short notes to quickly recall everything. So try to solve these two questions and then I will solve. Pause the video, try to solve this one and this one. Okay, these two questions, and then I will obviously solve in front of you. So let's start with this one. Okay, so what is this question telling? It is a very big question, so we have to read this. A pipeline processor has 4-stage instruction pipeline with the following stages. Instruction fetch, so it is a 4-stage pipeline and it has the following stages. First one is instruction fetch, then we have instruction decode, then we have execute, and then we have write back. So we don't have any operand fetch, right? What does the operand fetch happens? Intuitively I can say operand fetch should happen here in the instruction decode, here only, or in the execution. They haven't told me, right? The arithmetic operations as load and store operations are carried out in the execution. They will tell you what exactly what happens. Okay, so ALE operations, arithmetic operations are happening in the execution phase. The sequence of instructions corresponding to the statement S equals to R into P plus Q by T is given below. So sequence is given here, right? Okay, the value of the variables P, Q, R, S are stored in these registers before the execution of the instruction sequence. So they are stored somewhere in this register, general purpose register. This is a ALU. All these are in ALU, right? The number of read after write, raw dependencies, write after read dependencies, and write after write dependency in the sequence of instructions are given us. So you have to just identify how many read after write, that is raw, that is a true dependency. Remember, this is the true dependency. That is the actual problem for which I have to give stall cycles. And all these write after read, also known as I'm writing not after write. So what is write after read? It is a anti-dependency. Why? I have already read from it and then I'm writing, so it is not a problem. So that's why it is anti. It is opposite of dependency. It is not dependent. Okay, and write after write is false dependency, because I'm like, there is no dependency. There is a dependency that I'm writing again. I'm writing, but I only want to see the updated value, right? So it doesn't matter. That's why it is a false dependency. So we have to identify the number of var, raw, and wow. Okay, wow dependencies. So let's start with the raw dependencies, read after write. So here I'm observing that I have to first see where am I like, where are the dependencies? This is R5. Here I am writing and then I'm reading. So I am reading after writing. I am reading from R5 for this instruction multiplication. I'm reading from R5 after writing to it. So there is obviously a raw dependency here, right? So 1. Then again, if I observe here, again I'm reading from this register R6 to perform this operation after writing, right? Again there is a raw type operation. Okay, dependency, not operation, raw type dependency. Again if I observe this R4 is here, R5. Again this R5 is required, right, to perform this operation, and I am writing just before this instruction, right? So again I'm writing after, sorry, I'm reading after writing, so it is again a raw type dependency. Again here if I see, I'm reading directly, storing this value R6 in the X memory location. So obviously this value is written here and then I'm reading from it. So again there is another raw type dependencies. Total I have 4 raw type dependency. So obviously from the options you can see only in the one of the options there is present 4 raw dependencies. Option C will be correct, obviously, but we will obviously solve the other options as well. So this one was for the raw type dependency. Let's solve for the var dependency. Var, I'm going in a var. Okay, so write after read. So what you have to search? You have to search where I am writing after reading. So here if I observe, this is fine, this R2 is here. Okay, so okay, write after read, right? Write after read. So I'm searching for this. R4 is here. Okay, I'm writing after reading. So okay, just let me search few things here. If you see, I am reading from this R5 and then I'm writing after this instruction, right, which is not a problem. So I'm reading from R5 in the previous instruction and then I'm writing. So I'm writing after reading. Reading has been done, then I'm writing. So it is a var type dependency. Then here as well the same thing, right? Shortcut is, if arrow is like this, then it is a what type dependency. If arrow is like this, then it is a raw type dependency. Okay, but it is a what type. If arrow is like this coming from right to left, it is a war type dependency. If arrow coming from left to right, it is a raw type dependency. But I don't want you to just mug up the shortcut. I don't want you to do that. I want you to understand conceptually what is happening. So I'm reading after I'm writing after read, right? I'm writing after read. So I have already read this R5 value, then I'm writing on it. So it's a raw type it's a war type dependency. It's a tongue twister, sorry for that. Okay, here also same thing, right? I am writing on R6 after reading R6, right? After R6 read has been done. So again it is 1, so total 2. And here also, if you see, for wow type dependency, right? Wow type dependency, what will happen? The arrow will be something like this. So I'm writing after right. So here I'm writing R5, and again here also I'm writing R5. So it is a wow type dependency. Again, if I see here I'm writing on R6, again here I'm writing on R6. So again it is a wow type dependency. Total I have 2. So 4 to 2, option B will be correct. Pretty simple. I hope you understand. Just whatever is written, right, that you need to identify in the instructions. That's it. You have to search for that particular thing in the instructions. They have mentioned exactly what is raw. You don't have to remember the full form as well. They have told you read after write. They told you write after read. Everything they will give you in the question. Don't worry. They will give you. In today's GATE questions, they mostly give everything in the question. Okay, itself. Few things that my students understand that they need to remember. They understand that pain, so they don't tell you to remember everything. Okay, they just want to see the conceptual knowledge, whatever you have gained. That is the important point. So here is another question. So we have this following opcode and things are there. 5 instructions are there, and we have to perform 5 instructions, right? So what they are telling me, consider the following 3 statements. There is an anti-dependence between instruction I2, I5. Like they're talking about instruction I2, I5, and then they're talking about instruction I2, I4, and then they're talking within an instruction pipeline, an anti-dependence always creates one or more stalls. So here, right, first let's see the relationship between I2 and I5. I see I2 is here. This is my I2 and this is my I5. So what I observe is this instruction I2 and I5, right, has a write after write dependency. And what is called a write after write dependency? Write after write dependency, if you remember, it is called as false dependency. It is called as false dependency because actually there is no dependency, because I am writing, I have already written, then I am again writing, so it doesn't matter, right? If I write after, before, I am not reading from it, so it doesn't matter. Final value only matters. Okay, that's it. So it doesn't matter. And the second statement says that there is an anti-dependence between instruction I2 and I4. So if I observe I2 and I4, right, this I2 has R1 register, R3 registers here, and it has R3 registers here in the I4, right? So what is actually happening? I am writing after reading. So it is a raw type dependency, right? Sorry, not reading after writing. I'm writing, not raw, after reading. It is a var type dependency. I'm writing after reading. So reading has been done. Only the problem lies when I fetch the operand, when I try to read the operand, right? So reading already has been done. I'm writing after reading. So it is not a problem. So what type of dependency it was? It was anti-dependency, if you remember, because there was no problem. I'm writing only after reading. Reading has been done. I'm writing. So it is not actually a true dependency. I explained it is a anti-dependency, because if I swap the two, then there will be issue. Okay, if I swap the two, then there will be an issue. If I write after read, if I read after write, then there is a dependency, right? Then the write may not go through sometimes. So then there is a problem. But var is known as anti-dependence. So yeah, statement S2 is correct, that there is an anti-dependency between I2 and I4. But what about within an instruction pipeline, an anti-dependence always creates one or more stalls. Always is the important word, always. anti-dependence actually can create stalls. I have not explained that, but it can create stalls. Okay, anti-dependence, but not always. How we can create stalls? But let's say our instruction has many stages and we are not able to perform this read operation before this write operation, right? There can be a case. Okay, so we have to provide stalls, but they're telling me we have to always provide stalls. In most cases, this read operation will be done before this write operation, right? In most cases it will be done, so it is not necessarily true that I have to always provide stalls. Okay, so we'll see this with more questions. We'll solve those questions in the next lecture. We'll see this. Okay, so statement S3 is incorrect, statement S1 is incorrect, only statement S2 is the correct statement. Okay, so your option B will be correct. Okay, that I have an anti-dependence between instruction I4 and I2. So option B will be correct in this particular question. So that's it basically for this lecture. And in the next lecture, we'll learn about more types of hazards, that is branch hazards and control hazards. Okay, there are two types of hazards as well, branch and control hazards. So we will learn those hazards. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.